I can see.
Yes.
All right.
You're on mute, so yes.
Yeah, I think we'll just go ahead and get started.
Yeah.
I'm on mute now. So today we're going to be continuing our discussion on counting and probability. It's a big topic, so we need multiple classes to cover it. Let's get right into it. I suppose we want to count the number of ways to choose 2 apples from a set of 4 apples where order does not matter. And actually, assume the apples are distinguishable. So a better thing, kind of a better example is, let's say you want to choose, you have a group of 4 people and you want to choose 2 people to complete a task. How many ways are there to choose 2 people? Does anyone know the answer to that? Just want to shout it right off the bat. Anyone know? Let's see. Yeah, just say it out loud, guys. Just
6.
yeah. So okay, hold on. See, that's this. So well, yeah. So the order does not matter. So like apple 1, apple 2 is the same as apple 2, apple 1. Okay. Now call the 4 apples 1, 2, 3, and 4. We do casework based on the first apple and the pair we choose. These are the possibilities. Now you'll notice, of course, something like 3, 1 is not included. That's the same as 1, 3. That's what we mean by order not mattering. So with that in mind, then there are these 6 possibilities. Now what if you wanted to choose 5 apples? Then how many would there be? Take a minute to think about it, see if you can figure out, kind of using the similar strategy we used for the previous problem.
Yeah, so, again, if you want to send one of the hosts the answer, just make sure you're sending it to just one
Send it
of us.
privately, please.
Yeah. When we say casework on the first one, it just means if we're counting a pair, we just say, okay, what if 1 is part of the pair? Then what can the second possibilities be? If 2 is part of it, what can the second possibility be? And so on, and count that way. So we're just counting pairs of numbers from 1 through 5. So some people are saying 10.
So have you had people tell you the answer from? Or?
Yeah, some people are saying 10, but
Okay.
maybe we should wait a bit.
All right, I'll give it another 30 seconds here.
Yeah, more 10. Okay. You want to go ahead?
So yeah, these are our possibilities. So 1, 2, 1, 3, 1, 4, 1, 5. We don't do 2, 1 because that's already 1, 2, same thing. We have 3, 4, and 5, 3, 4, 3, 5, and 4, 5. That's a total of 10. Okay, so now we're going to look at the general case here. So how many ways can we choose 2 apples from n apples? Well, let's take a look at the possibilities. So we start with 1, 2, 1, 3, 1, 4, 1, 5, all the way to 1n, for how many ever there are. 2, 3, we obviously don't do 2, 1 or 2, 1 because that's the same as 1, 2. And 2, 2, well, we obviously don't do that. You can't choose the same one twice. All the way up to 2n. And then obviously we go 3, 4, 3, 5, all the way up to 3n. And then we start getting towards the end. We have n minus 2, comma n minus 1, and n minus 2n. And then n minus 1n. So that's the last 3 possibilities we list out. Now, obviously for n, there aren't any because there would just be nn, which obviously isn't allowed. We want to count the number of pairs that we have here.
Does somebody want to try and count the total number of pairs in the above list?
Yeah, so we're looking for a general formula for the number of ways to choose 2 apples from n apples. So we've got you started with listing out the pairs. How many of those pairs are there?
Yeah, so just take another like 20 seconds, 30 seconds.
Think about this. Remember the strategy we used for the last 2 problems.
Right, so some people are trying to count the total number of pairs in the above list, and
We'll just get right into it. So
Alright.
the first row, so we discussed this in the last lecture actually. How many are there in the first row? Well, 2 through n. So if we subtract 1 from all of that, we get 1 through n minus 1. So there are going to be n minus 1 apples here. And that makes sense because you can pair 1 with all the apples except 1 itself. That's n minus 1. For 2, well, it's going to be n minus 2, right? Because it's the same as 1, except you can't pair it with 2. That's going to be n minus 2. For 3, it's going to be n minus 3. And so on until 2 in the second to last row and 1 in the very last row. Now, in general, for the row k, you'd have n minus k apples. So this is n minus 1, n minus 2, and then n minus n minus 2, which is just 2, and n minus 1, which is just 1, okay? So how do we add this all up? Well, there are n minus 1 apples in the first row, n minus 2 in the second row, which we haven't shown all that here, 2 in the second to last row, and 1 in the last row. Now remember, the formula for adding up the first n positive integers, it's n times n plus 1 over 2. Here we're adding up everything to n minus 1, so it's n minus 1 times n minus 1 plus 1, which is just n all over 2. That's where that comes from. Okay, Ram, you want to take it from here?
Yeah, there's one more slide, which is just to say that confirm this with what we did for n equals 4 and n equals 5. So
yeah, for 4 apples and 5 apples, you can check that this is indeed a valid formula.
Yeah.
Okay, any questions so far?
Yeah, we'll take a break for about 30 seconds. Any questions, and then I'll.
Yes, so guys, so this what we're about to do is generalize this for more apples. So instead of 2 apples, if you wanted to choose 3 or 4 apples, we're going to show how you can figure out the number of ways you can choose that. So that's where we're going.
You want to stop sharing so I can share? Right, so as Suyash said, so our initial goal was to say, let's say we have n different apples. Actually, like Suyash said, n apples may not be such a good analogy, maybe n distinct people. Everybody's different, so n distinct apples, maybe they're all different colors, and we're trying to choose 2 of them. So I'll just go through this list one more time, because that's going to be the foundation of how we're going to count later. So we're trying to find 2 apples from n. So what if the first one is a 1? So the apples are 1, 2, 3, all the way till n. Well, okay, let's say one of the apples is a 1. Well, then what are the possibilities for the second apple? It can either be a 2, it can be a 3, all the way till n. Excuse me. If it's a 2, if one of the apples is a 2, well, the second apple can be a 1, but we already counted that because that's 1, 2. And then through n, and then as Suyash said, we can sum this up. So we have n minus 1, n minus 2, and so on. So we get this formula right here, which is n times n minus 1 over 2. Now this is a little interesting. Can we generalize this formula to, let's say we want to find the number of ways to choose 3 apples from n. What kind of formula will we get then? And yeah, this formula does match up with what we did for n equals 4 and n equals 5. So other than just finding, other than generalizing, if we want to just list it out, if that's one strategy for, let's say we want to find out the number of ways to choose 3 things from n, we can just list out all possible 3 tuples or 3 lists, but that is not very efficient, it's inefficient, and error prone, because we could just miss a possibility here or there. So, is there a faster way? Let's revisit the example. We want to find the number of ways to choose 2 apples from a set of 4 apples. Again, the apples are all different. Okay. So think of it this way. Instead of listing out each of the pairs, it's sort of similar idea to how we did the casework. There are 4 ways to choose the first apple. Okay. So we want to find a subset of 2. There are 4 ways to choose the first one. So if they're like A, B, C, D, we could choose C. There's 4 ways. Once we choose the first apple, there are 3 options remaining for the second apple. Once we choose 4 for the first apple, there's 3 options for the second apple. The reason for that is that, let's say we chose C, A, B, C, and D. Let's say we chose C for the first apple. Then the second apple can be either A, B, or D. In particular, it cannot be C. So there are 3 options left. So for example, C, B would be one possibility. Now, in the last class, we talked about multiplication. If there's, say, like A possibilities for something in A possibilities for something, and then B possibilities for each of those A possibilities, and the total number of ways is A times B. So then you'd say there are 4 times 3 ways to choose the pair, right? But if we go back, so 4 times 3 is 12. If we go back, we found there are 6 possibilities, not 12. So where did we go wrong? Again, I'll show this reasoning right here. Does somebody want to think about it? How did we get 6 in one case and 24, and 12 in this case? I'll give you a couple minutes to think about that. A hint is that order does not matter. So apple 1 and apple 2 is the same as apple 2 and apple 1. Okay. So some people are saying we overcounted. So where did we go wrong? In the multiplication 3 times 4, what we're really doing is we're saying, okay, let's say the first apple is a 1. So then we have 1, and then there's 3 possibilities: 1, 1, 2, 1, 3, or 1, 4. If it's 2, then it could be 2, 1, 2, 3, or 2, 4. Now already you can see a problem, which is that with a 2, we did 3 times 4 because for each of the starting positions, 1, 2, 3, or 4, there's 4 starting positions. There's 3 different cases after that. So we did 4 times 3. The issue here is that we're counting 1, 2, for example, along with 2, 1. We're counting both of these. Similarly, we have 2, 4, and we have 4, 2 as well. Backing up, remember, the problem we're trying to count is how many ways are there to choose 2 apples from a set of 4 distinct apples if order does not matter. So order does not matter means that apple 1, apple 2 is the same as apple 2, apple 1, which means that 1, 2 is the same as 2, 1. So this 12 is not actually accurate. We need to remove some of these to get the total number of distinct pairs that we can get. In particular, so we overcount. We should only keep 1 of 1, 2, and 2, 1, and so on. So actually, it turns out we can just divide by 2 to fix this error, because for any pair, say 2, 3, there's exactly one other pair which we do not want. When we have 2, 3, we do not want 3, 2. When we have 2, 4, we don't want 4, 2. For any pair A, B, B, A doesn't matter. So we divide by 2 because in the set of possibilities we have over here in the 3 times 4, we want to remove 1/2 of those because 1/2 of those are repeated. Somebody's asking, how do you know order doesn't matter? That's the way we set up the problem. The problem that we are trying to solve is how many ways are there to choose 2 apples from 4 apples if order does not matter. So that's just a thing we're imposing. If order does matter, then we actually don't have to divide at all. The answer would just be 3 times 4 because then we'd be counting ordered pairs for which we can choose 2 out of 4. So if order does matter, then it's just 3 times 4. But since order does not matter, we have to divide by 2 because exactly 1/2 of the possibilities are repeated. By the way, something I'll say right now, the handout has been uploaded. So if you're confused by anything we've done, you can ask us to back up or refer back to the handout. Okay. So therefore the count is 4 times 3 over 2 because we have to remove exactly 1/2 of these. And this makes sense because 6 is the answer we had before. Okay. So now the key with this method, let's just review this method. We said we're trying to find there's 4 possibilities for the first number, 3 for the second, and we divide by 2 because we're counting A, B, and B, A, both in this count. Okay. Can we generalize this? This method seems to be working quite well. We didn't have to list anything out. So suppose we want to choose 3 apples from a set of 7 where order does not matter. Again, order does not matter. Everything we're going to be doing regarding binomial coefficients, which is our current topic, order does not matter. So take a couple minutes to try and count this. And instead of giving us just a number, try and either explain how you got it or write down a formula which sort of tells that you understand. So take a couple minutes and try to use the previous method, not the listing out method. take another minute. All right. So again, the question is we want to choose 3 apples from a set of 7 where order does not matter. 7 apples are all distinct. So let's start off how we did before. There's 7 choices to the first apple since there's 7 apples initially. 6 for the second option. There's 6 options for the second apple because 1 is already chosen. Okay, so there's 6 apples remaining for the second option. And now those 2 are ruled out, so there's 5 options left for the third apple. So naively, before we remove for overcounting, we just say, okay, the total number of ways to choose through 3 apples, I should say apples there, is 7 times 6 times 5, because that's how we multiply and count it. Does this part make sense? And without overcounting, why it should be 7 times 6 times 5? In particular, why are we multiplying? Okay. Okay. Yeah, so 7 times 6 times 5. But now again, for each, now this one's a little more complicated. For each triple A, B, C, we count each permutation of A, comma, B, comma, C separately. So in this list of 7 times 6 times 5, we'd be counting 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. These are the 6 permutations of 1, 2, 3. We'd be counting all of these separately in the 7 times 6 times 5. Because in the 7 times 6 times 5 count over here, we'd say, okay, the first one can be a 3, the second one can be a 1, the third one can be a 2. That's perfectly valid. These are all different. We could also say, let the first one of the possibilities in the count is the first one is a 2, second one's a 3, third one's a 1. That's also a valid possibility. And all of these are counted, but we only want to count one of these because these are all the same up to ordering. So for any triple, there's exactly 6 of them because 3 factorial is 6. There's exactly 6 permutations which are all correspond to the same thing. So we want exactly one of those, which means we want 1/6 of the original count. Does that make sense? I'm gonna try and make a poll if that made sense. Maybe I'll do this next time. But yeah, did that make sense to everybody? Why we're taking 1/6? The reason for that is for every permutation, there's 3 factorial permutations. 3 factorial because that's 6, and we want to keep exactly one of those. Does that make sense to everybody? Just maybe say yes or no in the chat. In particular, if it does not make sense, then please speak up. I'm going to wait for about 20 seconds. All right. So the total number is 1/6, which means the number of ways is 7 times 6 times 5 over 3 factorial. Let me just explain why we had 3 factorial. The reason for that is for any permutation, a permutation is just a different way to order the same numbers. So for A, B, C, there's 3 factorial different ways to permute it because for the permutation, there's 3 choices for what the first element is, 2 for the second, and 1 for the third. So in general, a list of n elements has n factorial permutations. N factorial, remember, is n times n minus 1 times, and so on. Okay, so that's how we got 1/6. Now, in general, let's generalize. So if we want to choose k objects from a set of n, where order does not matter, there are this symbol. We call this n choose k. This is the n choose k binomial coefficient. And we claim the number of ways is this. This is similar to the formula we had before. The reasoning, I'm just going to explain it one more time for self-containedness. There are n ways to choose the first number. Remember, we want to choose k numbers, n minus 1 for the second, n minus 2 for the third, and so on, all the way till n minus k plus 1 for the kth object. The reason for that is that n minus 1, n minus 2, all the way till n minus k plus 1 is k numbers, all right? So then we multiply these together because these are all valid possibilities, which branch off of each other. So naively, there's this many possibilities, but for any tuple of k, for any set of k objects we choose, k factorial of them match the same thing. So we only want one of those k factorial in the final count. So the total count is 1 over k factorial like this, which is n times n minus 1 times all the way to n minus k plus 1 over k factorial. And that's defined to be this n choose k. This thing right here, it's like an n divided by k with parentheses around it, but with the bar removed. We call this n choose k. All right. And yes, somebody's asking, do the objects have to be distinguishable? Yes, they do have to be distinguishable. That just means that the n objects are all different. Color 1, color 2, color 3, and so on. If they're all indistinguishable, if we can't tell them apart, there's just one way to choose, because any k we choose is just the same thing. So the n objects are distinguishable. Okay, so this is n choose k. Now Suyash is going to get some practice with these binomial coefficients. Let's start the share.
Give me just a second, I'll have my screen up. Okay, here we are, binomial coefficients. So, okay, yeah, sorry. This we just covered. And now we're going to practice computing some binomial coefficients here in just a moment. But first of all, this was a big piece of theory, so I want to make sure you all understand this. So what we just went over here for 7 times 6 times 5 over 3 factorial, the reason we did that is because, so we have apples, there's 7 people, that's a better way to express it. And we want to choose 3 of them, but order doesn't matter. So you can choose, okay, so first of all, we have 7 choices for the first person we choose, okay? Now we can choose, we have 6 choices for the remaining people. So we can choose any one of those 6, and then 5 choices for the last person on, I don't know, what you want to call it, a group or a committee. So there are 7 times 6 times 5, but that takes order into account. Order doesn't matter though. So we want to divide by some number. Now what is that number? Well, for each permutation, for each possible kind of set of people that you could choose is counted 3 times. So let's say you chose persons 1, 2, and 3. Or then, so 1, 2, 3 is one of those combinations you had, but there's also 1, 2, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So that's why you divide by 6. And there are 3 factorial ways to rearrange it. So in general, it was 7 times 6 times 5 over 3 factorial. So it turns out this generalizes into a binomial coefficient. Now, Alan mentioned something in the chat that there is a more elegant way to express this. Unfortunately, we didn't write it down here. But it turns out that if you have n choose k, that is equal to n factorial. So notice we only go to n minus k plus 1, but if you went all the way down to 1, n factorial over k factorial times n minus k factorial. So you'll notice the missing numbers here. Let's see, we have something in the chat. And yeah, Ram just dropped it in the chat. So that is an equivalent expression, the same thing. And I'm pretty sure that's what Alan was referring to. Now, so you'll notice the numbers missing here are n minus k all the way down to 1. So if we put n minus k factorial in the denominator and in the numerator, then that's what we'll have. That's where that comes from. Now, so you can use that definition if you need to. Compute 5, choose 3. And send it privately to one of us in the chat when you think you've got it.
Yeah, so one thing I'll just say, the formula that Suyash mentioned is really important as well. We should have included that.
Yeah, so Ram has it in the chat, and that's much easier to use. Yeah. So,
but if you want to do it for computations like this, just remember that for the numerator, you start out with 5, and then you take the next 3 numbers. So 5, 4, 3, and then for the bottom, you take 3, and then all the way down to 1. So for n choose k, you take n minus 1, k numbers at the top, and then k minus 1 all the way to 1 on the bottom.
I'm going to give you guys about a minute to figure this out.
Yeah, just wanted to say that.
Did someone say something there? Or? Oh, never mind.
All right, I think a bunch of people are sending me the answers. You want to take it?
Okay, so 5 times 4 times 3. So remember, that's what he mentioned. Take the next 3 numbers and then divide it by 3 factorial. So you get 60 over 6, that's 10. Another way you could have done it is 5 factorial over 3 factorial times 2 factorial. So that comes out to 120 over 6 times 2, 120 over 12, that's also 10. All right, so kind of in terms of application here, that's if you had 5 people and you needed to choose 3 to complete a task for you, there would be 10 ways to choose 3 people. How about 5 choose 2? A few more seconds. This shouldn't be too challenging. So I've gotten a couple. I'm sure you've gotten a lot as well. So same idea. This time you only do 5 times 4 because you want 2 numbers over 2 factorial. 20 over 2 equals 10. You'll notice those produce the same results. Is that a coincidence? Absolutely not. Now let's do 6 choose 2 first. So for this one, so yeah, so there's the next 2 numbers down the line there, 6 times 5. Divide that by 2 factorial, that's 30 over 2, which is 15. Another way you could have done it is 6 factorial over 2 factorial times 4 factorial, because 6 minus 2 is 4. So that comes out to be 720 over 24 times 2. That's also equal to 15. It's 720 over 48, so 15. Let's see, 420. I have a trick question here, guys. Let's think about this one. Remember, 0 factorial is 1. That's important to know.
Some people are saying, is it 0? It's actually not quite 0.
If I had 4 people and I wanted to choose 0 of them, well, then there's only one thing I can do, choose no one. So it's 1, guys, okay? So 4 factorial over 0 factorial times 4 factorial, right? That's what I said is 4 choose 0 is 1. So, okay, some of you have already seen the next question. 4 choose 0 is 1 because 0 factorial is 1. So that just comes out to be 24 over 1 times 24, which is 1. How about 100 choose 99? So, again, we don't want to write out these hundreds of terms. So can you find a better way to do this? For this one, guys. So yeah, you could just do ellipses here. 100 times all the way to 2, that's 99 over 99 factorial. Now the 99 is in both, 98 is in both, 97, 96, all the way down to 2. You're just left with 100 over 1, which is 100. Now let's see. Oh, we don't actually have this. So very important concept here. So let's say I have 100 people and I want to choose 99 people to do a job. That's the same thing as choosing one person that doesn't come. So it's intuitively 100 choose 99 is the same as 100 choose 1. And obviously 100 choose 1 is 100. So that's the deal with 5 choose 3 and 5 choose 2, because 3 plus 2 is 5. So in general, n choose k is equal to n choose n minus k. So what was I gonna say? So remember that formula that we've talked about, n factorial over k factorial times n minus k factorial. If you switch out k for n minus k, well, k just becomes n minus k, and n minus k becomes just k. So it just switches, and you're still left with the same thing. So that's the math behind that. And yeah. All right, Rob, you'll take it from here?
Yep. You want to stop here?
Yeah.
All right. Yeah, so now that we have some practice with binomial coefficients, we're going to jump into an example. This is a bit of an involved example, but it's another pretty fundamental thing. We're going to be delving into the concept of stars and bars. And if you have any questions about how binomial coefficients work, this practice was meant to give you a bit of familiarity with that, but obviously if this is the first time you're seeing it, it could be confusing. So make sure you're letting one of us know if things are confusing to you. All right. So let's get on with this problem. Find the number of ordered tuples. Tuple just means list, by the way, of positive integers a, b, c. So positive integers means they're at least one, and their sum is 7. Okay. So take a couple minutes to try and understand the problem and think about how to attack it. And a key difference here from what we've been doing before is the word ordered. All right. Ordered means that 3, 3, 1, for example, is different from 3, 1, 3. They obviously only differ in the order they're written in, but we consider them different. This problem, if you replace this word with unordered, so 3, 3, 1 is is the same as 3, 1, 3, then that problem is very, very difficult. So we're going to be dealing with the problem. Assume that the lists are ordered, and how will you calculate the number of triples a, b, c? So I'm going to give everybody a minute to think about the problem. Make sure you understand it. If the problem is confusing, please let us know in the chat, because otherwise what's going to follow is going to be even more confusing. Okay. Yeah, so the first approach we're going to present is, well, the numbers are pretty small. Obviously, the second method we're going to talk about is a more systematic approach, and that can be generalized to tuples that are longer than 3, and 7 is a bigger number. But currently, the numbers are small enough that we can just brute force it out. Brute force just means write out every possible tuple. So the possibilities are 1, 1, 5. So basically, the way we're going to attack this brute force is by casework. So actually, I'm not going to show it. You might have already seen a bit, but try and list out the possibilities, and can anybody figure it out? The number. Remember, they're positive integers, so we can't have any of them being 0. Let me just show the brute force, actually. So we can start with, let's do casework on, again, the first element, all right? So if the first element's a 1, then it can be 1, 5, 2, 4, 3, 3, because the next two elements have to sum to 6. So 1, 5, 2, 4, 3, 3, 4, 2, or 5, 1. If the first element's a 2, now look, 2, 1, 4 and 1, 2, 4 both appear, but that is fine. This is different from the previous example, like Suyash said in the chat. 2, 1, 4 is different from 1, 2, 4 because order matters. All right. So 2, then the next two have to sum to 5. So 1, 4, 2, 3, 3, 2, 4, 1. 3, you have 1, 3, 2, 2, 3, 1. 4, you have 2, and then 5, you have 1. So the total number of possibilities is 5 plus 4 plus 3 plus 2 plus 1, which is 15. But is there a more systematic approach to this? What if we made the numbers a lot bigger? Or if we made the lists longer than 3, then could we still do it? So we're going to try and attack the same problem, not make the numbers too big, but use a systematic approach. So suppose person A gets A apples, B gets B apples, C gets C apples, and we know there are a total of 7 apples, okay? And each person can get any integer number of apples at least. Now, what we're going to do, we're going to represent the apples. We're creating a new analogy here. So this problem was just algebraic. And now we're saying, okay, let's say we have ABC, create person ABC and give them some apples, A, B, and C in particular. Now, this is very different from the previous example because these apples are indistinguishable. So for example, what we're going to do is represent the apples by a list of dots. Don't read into this too much, actually. Well, what we're going to do is the apples are indistinguishable, which means that we're not going to distinguish if, person A gets this apple versus that apple. All that matters is the number of apples you have, okay? So now what we're going to do is in this list of dots, so we have 7 dots, we're going to place 2 dividers between these dots, which is going to represent, this is A's value, this is, so for example, let's say the dividers are here and here, then A gets the first 2, B gets the next 4, and C gets the last one. So these bars are just a way to represent how A and B are, A, B, and C split up the apples. So again, if A plus B plus C is 7, that just corresponds to some way to put the dividers between these dots. Does that make sense, everybody? We're just creating an analogy, and then this is going to be easier to solve. I'm going to wait for 20 seconds, just so you can read this slide and make sure you understand what's going on. So we're given a tuple A, B, C, say which sums to 7, and there's a unique way to represent that using the dots. So A gets the first run of dots, B gets the second run of dots. Run just means a subset of the dots between the divisors. So it's just like a run of them. B gets the second run, and C gets the last run. So this example right here corresponds to 2, 4, and 1. Okay. Now the key utility here, and yeah, the dots represent the 7 apples. We can represent any partition of dots by putting 2 dividers. Again, we're putting 2 dividers because 2 dividers makes 3 runs of dots. 2 dividers, this is the first run, this is the second run, and this is the last run. So 2 dividers gives us 3 different runs. So now the number of tuples, in particular A, B, C, is the same as the number of ways to place 2 divisors. So now we're just counting. Actually, let me back up here. Does this example make sense to everybody? The dots are representing distinguishable. The dots are representing indistinguishable apples. So it doesn't matter if I say like switch these 2 dots, you still can't tell the difference. The dots are indistinguishable. In that sense, the apples carrying over the apples analogy maybe wasn't the clearest, but okay. So now we just want to count the number of ways to put 2 dividers between these 7 dots. There's 6 valid spots for a given divider because there's 7 dots and there's between these are the 6 possible ways. Since each run must be length at least 1 because they're positive integers, the dividers must appear between the dots. In particular, the dividers cannot appear to the left of the dots or to the right. So these red lines are where the dividers can appear. And now we just need to count the number of ways to place two dividers in 6 spots. Because let's say we put the divider here at this red spot on the rightmost and on the leftmost, and that would correspond to 1, 5, 1. Let's say you told me one of the possibilities is 3, 3, 1. That would correspond to putting a divider here. And anyways, 3, 3, 1 would correspond to putting one divider right here and one right here. All right, because that would be 3, 3, and 1. Now, this is pretty clever because now it just suffices to count the number of ways to put two dividers in these 6 places, which is just 6 choose 2. 6 choose 2 because if I put a divider here, say like here and here, that's the same as putting it in this different order because the dividers are obviously indistinguishable. So the concept of distinguishable and indistinguishable is really important, okay? The dividers it doesn't matter if I put divider 1 and divider 2 in the same spot or switch spots. All that matters is I'm putting them at 2 separate places. Obviously, we can't put the 2 dividers at the same spot because that would correspond to a run of length 0. So the total number of ways is 6 choose 2. This last step is a bit confusing, the exact details of the one-to-one correspondence. But again, you can refer to the handout if it's confusing or if there's any questions you have right now. Feel free to ask. I'm going to pause here for about 1 minute. And yeah, in particular, note that 15, 6 choose 2 is 15. This is the same as the brute force count we did up here, 15 possibilities. So that matches up. Yeah, as Alan was saying, we can generalize this method to even if A, B, C are not positive integers. In particular, if A, B, and C are at least 0 instead of at least 1, well, that's a question for a different day. But I'm going to pause for about 20 more seconds to see if there's questions about this. Just make sure you just read through this slide again. There are going to be a lot of problems about stars and bars in the practice problems. This is a very important concept, and there's adaptations of it. So it's not just changing up the numbers with the same sign. Yeah, so here somebody's asking, in stars and bars, the subset sizes are not fixed. That is correct. The sizes are not fixed. We are placing bars and we can get any set. Okay, so I hope that made sense. Now we're going to skip to a topic outside of binomial coefficients. What we've covered till here, though, is the most important. This stuff is really, really important to understand, and it appears a lot in different ways, not just in these sort of vanilla ways. But now we'll be talking about different approaches that can be used in counting and probability problems. If there's any questions, feel free to ask, but Suyash, you want to take it over?
Yes, okay, so hold on, let me share my screen. Okay, so continuing on with counting, I realized we talked about counting and probability, but there wasn't really much probability today. So we're now going to talk about another useful counting technique called complementary counting. So in some cases, rather than counting the number of desired outcomes, it is easier to count the number of total outcomes and the number of bad outcomes, and then subtract that from the number of total outcomes. This is best explained with an example. Let's take a look here. So, fairly recent problem, AMC 10B 2018, problem 5. How many subsets of 2, 3, 4, 5, 6, 7, 8, 9 contain at least one prime number? Take a few minutes to think about it. If you don't get it right away, that's okay. We'll show kind of what complementary counting is in this problem and how it's useful. But go ahead and take a moment to think about it.
All right, some people are getting how to do it. I guess we could wait another 30 seconds.
In the chat. Okay, so let's go over this. So first of all, rather than finding the number of subsets that contain at least one prime number, there isn't a straightforward path to do that directly. But what if we find the number of subsets that don't contain a prime number? Then if we find the number of total possible subsets, we can just subtract that and we can get the answer. So first, let's find the total subsets. Now, we discussed this with the condiments problem last week. For each condiment on the hamburger, you could either include it or don't include it. Well, it's essentially the same concept here. For each element in the set, if you're trying to form a subset, you can either include it or not include it. So since there are 8 elements and 2 options for each, there are 2 to the 8th subsets, 256. Now we'll subtract the number of subsets with no prime number. If you think about it, the numbers here that are not prime are 4, 6, 8, and 9. So if the subset is any subset of that, then of course it's not going to have a prime number. So if it's all subsets without primes are going to be subsets of that 4, 6, 8, 9 set, and that includes the empty set as well. So that will get subtracted out. Now, again, there are 4 elements here, so they're going to be 16 subsets. Because again, for each element, you either include it or don't include it. So now all that's left is we do 256 minus 16, 240 subsets. Now, FYI, I missed this problem because I forgot that 2 was a prime number. So I think that's it. So Ron, want to go over this last example if you have time?
Yeah, it's important to remember that we want to only count the primes and composites and just separate them, and then it's easy from there. All right. We have one more example, which is going to be sort of a casework problem involving probability. So this was one technique, complementary counting. Obviously, in class, we don't have that much time to go over many different examples since we're trying to spend more time on each, but there's going to be more of that in the practice problems, which are in the handout that has been posted. But for now, we're just going to go over one more concept, which is casework. So why don't you take a couple minutes to read over this problem and attempt it. We're going to reconvene in 2 minutes and see what you have. This is from the AIME a few years ago, an early prompt from there. Again, think how to use casework to do this problem.
As a hint for casework, so kind of in terms of yeah, an urn is just a bowl.
Yeah, casework just means somebody's asking what does casework mean.
Yeah, so like I guess, or you want to say something?
No, go ahead.
I'm saying so like so when you say that drawing both balls are the same color, it can either be both green or both blue. So those are probably the cases you want to consider here.
Right. Yeah, casework just means splitting your desired outcome into cases that are easier to handle individually, and you can add those up.
Yeah, so sometimes the key to solving problems like this is dividing it into the right cases to analyze.
Okay, we're going to take 1 more minute. All right. So let's just go over the problem really quick. So you have two bowls. One of them has 4 green and 6 blue, and the second has 16 green and n blue. You take each of the bowls and you draw one ball from each of them. So you have 2 balls. What is the probability, or you're given that the probability that both balls are of the same color, either both green or both blue, is 0.58. Find n. All right, so the two cases here, we want to narrow in on this sentence right here, which is that the probability that both balls are of the same color is 0.58. Since they're of the same color, they can either be both green or both blue. So we do casework based on the color of both balls, given that they're the same. Case 1, both balls are green. Well, we want to find the probability that this case happens. So the probability that the first ball is green is 4/10, because the first bowl has 4 green and 6 blue, so it has 4 green and a total of 10. So the probability that we draw a single green ball is 4/10. There's 10 balls, 4 of them are green. And probably the second one is green is 16/16 plus n, because the second bowl urn has 16 green and a total of 16 plus n. So the fact that all that matters is there's a total of 16 plus n, and there's 16. So you can think about it like, let's say I have one red ball in a group of a total of 10 balls. Then the probability that I draw the red ball is 1/10. So 16/16 plus n. And since we want both balls to be green, we need to multiply these probabilities. That's like saying, let's say I have one urn which has one red and out of a total of 10, and a second which has one red out of a total of 10. The probability I draw one red in both is 1/10 times 1/10. So here we do the probability of this case is the product, which is 4/10 times 16/16 plus n. Does that make sense to everybody? We're multiplying because we want both to be green. That's the case we're working in. All right. The second case is very similar. Both are blue. The probability the first ball is now 6/10. This should be blue right here. So 6/10, and the second is n/16 plus n, because now there's n blue balls and a total of 16 plus n. So the probability of this case overall is the product of these two, which is 6/10 times n/16 plus n. Now, since these two cases are separate, the total probability of one of these happening is their sum, which we can compute to be this. It's 4/10 times 16/16 plus n plus this, which simplifies to 64 plus 6n over 10 times 16 plus n. We're given, go back to the problem, that this probability is 0.58. So now we have an equation from which we can solve for n. So recapping, we were using n. We found in terms of n, the probability that we draw either both green or both blue, and we summed up those probabilities and we're setting it to 0.58 to solve for n. All right. Setting this equal, we get an equation, try to finish. We have about 2 minutes left, so maybe we're not going to wait too much, but from here, just algebra, no counting the probability concepts left. We set this to 0.58 and solve for n. So you get cross multiplying, you get 100 times 64 plus 6n is 58 times 10 times 16 plus n. Expanding both sides gives you 6400 plus 600n is this side, so it's just a linear equation. And from here you can solve for n pretty easily to be 144. All right, so just let's recap the main ideas. The algebra at the end was relatively straightforward if we got to that step. So right here, the probability that both balls are the same color. So it's hard to deal with this on its own. You know, how are you going to say they're the same color? But if we can break it down into two cases, which is they're either both blue or both green, well, then it's easy to do because we are given the compositions of both of the bowls and we can just compute the probabilities. Again, the reason we multiplied is because we want both balls. That's the case we're in, which is that both balls are green. So we have to multiply the two probabilities to be sure that the entire pair that we drew are both green, because probably the first one is green is 4 over 10, second is 16 over 16 plus n. You multiply those, and we add them up because those are the two cases. All right. So this problem was more about casework, and it also involved some probability. If it was confusing, any of what we did today in class was confusing, the handout, feel free to review that, and throughout the week, make sure you go through the handout and try and work on some of the practice problems. Again, feel free to email any of us. Email the Pacific Math Association email ID if you have any questions. And yeah, is there anything else you can think of, Suyash?
No, just thanks for coming today, and we'll see you all next week.
Yeah. Class will be next
Definitely.
week.
Thank you for coming.
All right. Thank you, everybody.
Bye.